Okay, in our chapter on powers, it's definitely going to take a little turn here, and we're going to go back and discuss something called sequences. Now, we did arithmetic sequences, and now we're looking at having to do what's called geometric sequences. We will again do them explicitly and recursively, just like we did arithmetic sequences back in earlier chapters, and then we'll obviously solve real-world problems with them. So, let's get started. Here is our learning goal, stated another way, but here is where our geometric system sequences take place. By definition, we have each term after the first is found by multiplying the previous term by a constant. So when we had our arithmetic sequences, we were adding or subtracting to get, or we were adding a positive number or adding a negative number, which is like subtracting, to get the next term. So in these, the key piece will be multiplying by that constant. So in your work, check it. You're going to need to make sure these sequence of numbers have some multiplication going on in them. In the recursive look, we've done two types, remember, recursive and explicit. In the recursive look, you have a two-statement equation. G sub 1, or the first geometric number in the term, or first term in the sequence, will be a number. That'll be given to you, so some number. Then every other term in that sequence. So as I start saying this, think about what I'm doing. I'll put a little dot as I say it. So every other term in that sequence will be calculated by taking the constant rate times that previous term. And remember, this for integers n greater than or equal to 2 is basically said when I say for all other terms in my sequence. For integers n greater than or equal to 2, that means I could do this for the second term in the sequence, the third term in the sequence, fourth term in the sequence, fifth term in the sequence, sixth term. So this calculation, R, that constant ratio, that constant rate, and that's what the R stands for. So think of it that way. So let's reset that, and we say, think of it as that constant rate or ratio between the numbers. Okay, so that's what that is. R is that non-zero multiplier, and G1 was that first term in our sequence. So keep that in mind. It's going to be a multiplication that gets us between terms in these. All right. Explicit formula looks more like G sub n, any term in my sequence, will be calculated by taking the first term, multiplying by that constant rate, but one less than the term you're on. So think about this. If I say write the first 6 terms of a geometric sequence in which G sub 1 equals 6 and R equals -2, we would have some sequences here. I don't know why these ended up being, they look like they're a bunch of blanks, but let's just make them look more solid. Okay, so it says, write the first 6 terms. So these would be the blanks for the first 6 terms of sequence, in which G sub 1 is 6. Okay, we can do that. And our constant difference is, constant rate, is a -2. So you know that rate is your multiplier, so all we have to do is take our first term, 6, times it by -2, we get -12. Now take -12 times it by -2, we get positive 24. It's a little different than what we've seen before. We have a positive-negative look in our sequence. Times 24 by -2, we get a -48. Times -2 times -48, we get a positive 96. And then 96 times a -2, we get a -192. So there are the first 6 terms. You'll notice they are alternating positive, negative, because our R value, our multiplication, our multiplier, was a -2. which then causes it to toggle back and forth. So all we needed was the G sub 1 term and an R value to write the sequence. We should also be able to go back up, just as a quick review, and write the equation. So let's do that. G sub n, any term in my sequence should have been equal to my first term, which was my 6, times R, negative 2, to the power of how many multiplications, and this is where it comes from. How many multiplications did I really do? I have 6 terms here, but look at my little check marks. I only multiplied 5 times to get 6, because you're going from the first to the second, that's 1, second to the third, 2, third to the fourth, 3, fourth to the fifth, 4, fifth to the sixth, 5. So it's n minus 1 in this case, n, number of terms was 6. 6 minus 1 is 1 less than the number of terms you need, because you only have 5 multiplications to do to get the 6 terms there. That's the key on this geometric explicit setup, and that is your exponent. Okay. So each one of those, obviously, if you wanted the first term, you'd put a 1 in. If you wanted the, we were doing the 6th term right here, so we really should have probably, get our eraser out, let's not make it so big so it wipes everything out. This would say G sub 6. So if I wanted just that 6th term, it would be 6 times negative 2 times the power of 6 minus 1, which was 5. Okay? Write the first 5 terms of the sequence defined by the following equation. Now look at it carefully. I'll move it up a little. First 5 terms of the sequence. So 1, 2, 3, 4, 5. Now if you can look at that equation and it matches our setup exactly, then you should be able to tell me what our first term is. If you can't, then you put a 1 in for n and you do the arithmetic. So right now our first term is 4, because this matches our setup exactly. And so now we can calculate and do our second term, because that's what this is basically. So we'd put a 2 in. 2 minus 1 is 1, so our power is 1. 3 to the first power is 3. 4 times 3 is 12. Now you can see that that was a multiply by 3. So if you can see that in your group, so now you could just continue and multiply by 3 rather than having to do the calculation every time. So 12 times 3, 36. 36 times 3, do the math. 3 times 6 is 18, carry the 1, 108. And 3 times 108 is 324. So there are your first 5 terms for that sequence. Okay, from here, let's go one step further and do something that is a real world example that we may need. Okay, let's close this again. Let's assume we've got a big combination here. Here's our geometric explicit equation. Suppose a ball is dropped from a height of 100 feet and bounces to 80% of its previous height after each bounce. Find the height that the ball reaches after the 10th bounce. So obviously this ball is going to keep bouncing. Now I want you to look. So when we started, we knew that this height was 100. And it bounces to 80% of its previous height. So right now it has not bounced when it's sitting here at 100. But here is the first bounce. Here is the second bounce, third bounce, and et cetera, and we need to do that for 10 times. So read carefully, and it says bounces to 80% of its previous height. So yes, 80% of 100, so you know that that next one was a height of 80. But look at what they want us to find the sequence of. After each bounce, find the height the ball reaches after the 10th bounce. So really, after the first bounce is right there. After the second bounce is right there. That is our sequence. So we could write all 10 of them out, but in this case, if we're just looking for one particular value, which we're looking for, what is the height of the ball on the 10th bounce, then we should be doing G sub 10 equals, our first term in our sequence would have been that 80, not the 100. The 100 was initial height. it had not bounced there. It bounces and it goes up to 80. And since it says find the height of the ball reaches after the 10th bounce, that'd be like saying first term should be after the first bounce, after the second bounce, after. So we've got an 80 for G sub 1. Then we know our multiplier is a 0.8, standing for the decimal that 80% represents. And then at n minus 1, we've got our 10. 10 minus 1 is 9. So do the math, either with your calculator or not. And let's go, I don't have exponents on this one, so let's go back and close that. Just use your graphing calculator. And you've got a 0.8 to the power of 9. And that has to be multiplied by that 80. You could do that all at once. So we are now looking at, what was this, 100 feet originally? The ball would only be at 10.74-ish feet after the 10th bounce. Okay? So real life situation that you can use on your problems there. Okay. I think we'll be okay with these. And 2 new formulas. Let me go back to each of those pages just briefly so that you can see the 2 different formulas we're going to be using. This was the explicit because it took us right there. Okay, the one we used up here. I'm going to reset this page, make it a little cleaner for you. So G sub n equals G sub 1 times r to the power of n minus 1. And then back to this page for when we have the recursive version, where you have to write G sub 1 is your first term, G sub n equals your rate times your previous term for all integers greater than or equal to 2. All right, so you should be able to look at those, and it should kick in from what we had done previously with arithmetics. So if not, bring those questions with you to class.